Visible?
Yep.
All right. Hi, good afternoon, morning, evening, everyone. Welcome to my virtual presentation on online shape and pose estimation from contact sensing. I'm Sudharshan Suresh. I'm a PhD student at the Robot Perception Lab of Carnegie Mellon. I'm broadly interested in statistical methods for state estimation and perception. So today's presentation would be in that direction. As a high-level motivation, tactile measurements give us a good understanding of shape and pose of unknown objects. Humans are excellent at this, at haptic identification, and studies show that they can identify 96% of classes of objects when blindfolded, and global shape is cited to be a key factor for this. One key insight is that tactile exploration is analogous to the SLAM problem, in that it's intrusive in nature and a chicken or egg kind of problem where a good object model is needed for pose estimation, but good pose estimates are needed to improve the model with sparse measurements that we have. So you need one for the other. How we formulate the problem here is that given a movable 2D rigid object on a frictional plane, we wish to get both shape and pose information from a stream of tactile data. So specifically, here, we want to achieve some sort of probabilistic representation of the shape of the object. And we want to figure out how do we do this inference online and efficiently. To go towards the question of shape representation, we think about using Gaussian process implicit surfaces, which plainly put are regressors that learn a shape representation from sparse contact points and normals to an actual function that represents the surface of the object. So for example, the image on the right here tries to represent this object using a potential function. And the zero level set there defines what the implicit surface of the object is. So it's continuous, it's non-parametric, and it's pretty nice to use. There's a good breadth of work that uses this for known pose mapping for 2D and 3D settings. So now we want to put this, tie it into like a SLAM-like representation. So we perform a least squares optimization similar to prior work from you and others. There are a few differences here in terms of theirs was a batch formulation where they recover poses and shapes after the fact, and their shape model was a piecewise linear model, whereas here we're trying for a non-parametric model. And we carry out these this inference efficiently online on this graph structure using what we call as incremental smoothing and mapping. And what our factor graph or our graphical model represents are the constraints in the problem. We have physics-based constraints on quasi-static pushing using an ellipsoidal limit surface approximation. We have contact constraints that ensure that the contact point and normal directions are agreeable to the current model we have. And we update the shape contour from the Gaussian process probabilistically at every iteration. And this GP and factor graph optimization step is performed back and forth to get online estimates of the shape and pose of the objects. To evaluate this, we give some tactile exploration simulations where we employ contour following and we collect the result in tactile stream of contacts and normals. We do this for a range of time steps and add Gaussian noise to these shapes that we have. The final shape contours and the planar pose estimates over time are shown here. And these are solved efficiently, incrementally, and online. And we see a combination of physics-based reasoning and contact penalties that constrain the pose, while the contact data updates the Gaussian process or what we know the shape to be. For a quantitative comparison, we use a modified Hausdorff distance metric to compare the shape contour with the ground truth, which captures both the shape and pose errors over time on a global frame. And we see that there's a steady decrease in the error over time, while further jumps can be attributed to pose drift in the optimization. So looking towards future work, we want to incorporate global constraints such as vision and experiment with richer tactile data and other pusher configurations. We believe that there's some underestimates and overfittings in the results we have, and tighter integration of the Gaussian process with the factor graph formulation can solve this. And we also want to delve into the theoretical correctness of the contact constraints. Thank you for your time. For the full story, you can check out our paper in the workshop proceedings and reach out to me for any more information, and you can use the chat to ask me questions. Thanks.
Thank you.